Hi, and welcome to the Vivado HLS, an example of hardware acceleration lesson. In today's video, I will show you how to make hardware acceleration with a 2D non-separable filter implemented in Vivado HLS. Then I will show you different techniques for optimization of the implemented 2D non-separable filter for increasing significantly hardware acceleration. I would like to start from the theory of operation of the 2D non-separable filter in Vivado HLS. It's not just simple theory, it's a theory regarding Vivado HLS resources. So here we have input and output image. For reading and writing images we will use axis stream interface, where the data will be read or writing pixel by pixel, and every pixel is represented by 16 bits. Then in Vivado HLS we have line buffer. Line buffer is a set of lines, and every line is represented by a BRAM memory. So size of every line, it's just size of one row of the input image. Then we have two elements like window and kernel. It's arrays, and this arrays is implemented as just register memory, so it's not a BRAM. In kernel array we will keep our coefficients for the 2D non-separable filter. In the window, data will be read from line buffer. After reading data from line buffer to window, and after multiplication by kernel coefficients, all data in window will be summarized and output to the output image. Let's consider how we'll operate our 2D non-separable filter. So first of all, we start from reading input image into line buffer. Pay attention please that we just update line buffer 0, and others lines will be updated automatically. So this is the way how line buffer works. What about window? In window we just fill data from line buffer, from every line. So it means that every row in window will operate just like FIFO, so first input, first output. Data in our window will be multiplied by kernel coefficients. In my example, all coefficients is equal to 1, but of course for 2D non-separable filter this array can consist any kind of coefficients. And finally, multiply the data that is kept in the window, we'll summarize it, and then we'll output to the output image by using axis stream interface. Okay, so let's go to Vivado HLS and see how to implement 2D non-separable filter. So in my Vivado HLS I have several files. First of all, it's a header file, it's a file with algorithms, and it's a test bench file. So here I have three implementation of the 2D non-separable filter. First implementation, it's just a direct or naive implementation. Two others, it's a kind of optimized implementation. It's a kind of optimized of the naive implementation of the 2D non-separable filter. So I will start from direct implementation. I will show you how long it takes to compute entire frame, the size of frame, and then we will turn to optimized optimization of the 2D non-separable filter, and we will see how fast it becomes when we using different techniques for optimization. And of course I will show you what kind of techniques, optimization techniques could be applied to the 2D non-separable filter. So direct implementation is quite naive. So in direct implementation, I just have input and output stream interfaces. It's an axis stream with the width of the input and output data equal to 16th bit. Then here I declare line buffer and window. Size line buffer equal kernel size and the width of the input image. So size of window is equal to the size of the kernel. Actually, kernel I have here, so it's just a static array. Here I declare two axis stream output and input channels. So, what is a direct or naive implementation of the 2D non-separable filter? It's just two loops. Every loop just count rows and calls, inside of these two loops I just read input data into one variable, and then I write this variable to my line buffers. So actually here I just write input data, and this declaration allows makes my line buffer works as you could see from presentation. So it means that every new data I will write into line 0, and other lines will be upgraded automatically, and data from other lines will be read to the next line. So for doing this, you just need to write to declare line buffers as well. Yeah, like this. And here we have two inner loops. It's two inner loops where I just read data from line buffer, multiply this data on my kernel, and insert multiplied data into the window. After I finish doing multiplication, I just will transfer my window to the sum window, where I just make a sum, where I just find the sum of all coefficients of the window. It can be seen from the code. And summarize the data, I just will write out to the output side data channel, and by the way, here I am declare the last signal, so it means that the last signal will be applied on the last pixel in the frame. So let's start from C simulation. Okay, it takes a couple of minutes. Okay, so we finished C simulation, and here in this bench I have input image, and my test bench will produce two output image that could be read by MATLAB script. In MATLAB script, I just compare software or MATLAB implementation of the 2D non-separable filter, and hardware implementation for both optimized and non-optimized implementation of the 2D non-separable filter. So here I have just this is my input image. Let me magnify, yeah, and this is my outputs. This is a software output, so it's output image that is calculated by using MATLAB, and this is my hardware output. It's from a direct implementation of the 2D non-separable filter, and here I have output image from optimized implementation of the 2D non-separable filter. So as we have all these three frames, we can compare, and we can see that any implementation software or hardware implementation give us equal results. Okay, so let's go back to our Vivado HLS direct implementation, and let's run C synthesis. We will run C synthesis for direct implementation of the 2D non-separable filter. Here we have synthesis report for direct implementation of the 2D non-separable filter. So let's take a look on several points in the report. First of all, of course, it's resources. As you can see that our Vivado HLS algorithm takes just RAM memory, because as I told you before, line buffers in Vivado HLS implemented as RAM memory. Then let's consider and by the way, here we don't have DSP blocks because actually our coefficient is static, so it means that it doesn't make sense to implement multiplication by using DSP block. But of course, if you will use kernel just outside, for example, by using Axelite interface, in this case, multiplication will be implemented by using DSP blocks. So, okay, timings. What about timings? Latency of the 2D non-separable filter direct implementation shows how long it takes to compute entire frame. So let's calculate how long it takes in seconds. Just we will take latency, it's in clocks, and we'll multiply by 5 nanoseconds. Okay, so it means that direct implementation takes about 63 milliseconds for processing entire frame, and the size of frame is 2048 by 1536. So let's write down this result. Okay, so here I have a file, and I just will write down that direct implementation takes 63 milliseconds. Why so long? Actually, we can see loops, and in loops we have a very important parameter. It's our initiation interval, and as you can see, it marks in red. Why actually red? Because we were targeted to get initiation interval equal to 1, but actually it takes more than 1. It takes 4 clocks. What does it mean? And why actually 4? Let's take a look in our direct implementation, and here you can see that I insert Pragma pipeline. So it means that Vivado HLS will try to unroll all internal loops. But as I told you before, as we have line buffers implemented as BRAM memory, and BRAM memory in Xilinx has only 2 ports, so it means that in 1 clock we just can read no more than 2 operations, write or read. But here we are reading, so it means that only 1 internal loop will be unrolled, but other internal loop, I mean this external loop, won't be unrolled. So what does it mean? It means that our algorithm will wait for these row loops before it can apply new data. So it means that initiation interval shows that we can have new data, input data every 4th clock, but not every 1 clock as we were targeted. And how can we improve of the implementation of the 2D non-separable filter for reducing initiation interval and for increasing throughput of the algorithm? So There are several techniques. I will show you main two techniques. One technique, of course, it's a closed domain crossing. It's when we just read data in a slow clock and then dealing with the clock in 2 times faster. For doing this, we need to use XStream data FIFO, whereas we can apply slow clock on slave interface and faster clock in the master interface. Another technique is a very useful technique and widespread technique. It's of course data with conversion. What does it mean? For example, in Zynq Ultrascale Plus we can operate up to 128 bits of bus width. So it means that if we have data, input data equal with width about 32 bits, it means that we can combine in one word, and in this case we just can have every new word every 4th clock. So actually both of these techniques could be combined and they could be used for increasing throughput for XStream data flow. So I go back to Vivado HLS. So in Vivado HLS, in field 2D fast implementation of the 2D non-separable filter, I am using data with conversion. So it means that I will accept data width equal to 128. So it means that I have 8 points. I have 8 points in one word. So in field 2D opt function, I implement like in direct algorithm, like in direct implementation, but with reducing initiation interval. So just let's run synthesis of the optimized version 2D non-separable filter. Okay, so here we will change to optimized version. And let's run it. Let's take a look on synthesis report for optimized version of the 2D non-separable filter. So resources is almost the same as from direct implementation, but let's pay attention on latency. Latency is much less than direct implementation. Let's calculate how long it takes for computing entire frame. So just will multiply by 5 nanoseconds. Okay, so it means that reducing initiation interval allow us to increase throughput of the 2D non-separable filter. It means that it takes only 16 milliseconds for computing entire frame. It's much faster and 4 times faster than direct implementation. Yeah, and you can see initiation interval right now is equal to 1. So again, in this implementation of the 2D non-separable filter, I just reduce initiation interval, and but all others data, I mean, for example, stream data, output stream data width, input stream data width, is the same like in a direct implementation. Right now let's consider how fast will be fast implementation. It's a third function, fast implementation of the 2D non-separable filter. Let's run this synthesis. Here we have a synthesis report for the fast implementation of the 2D non-separable filter. Okay, so about resources, it's almost the same, and let's consider how fast is it. Okay, so here we have 3, 1, and we will multiply by 5. Okay, so it means that fast implementation of the 2D non-separable filter takes about 2 milliseconds for computer entire frame. Okay, let's run down 2 milliseconds. Okay, so here you can see that direct implementation took about 63 milliseconds. Then after I reduce initiation interval, it become equal to 16 milliseconds. And finally, when I use fast implementation of the 2D non-separable filter, it takes only 2 milliseconds to compute entire frame. Let's summarize all information that I give you today about implementation of the 2D non-separable filter in Vivado HLS. So here you can find, this is my code. Here I have 3 types of implementation of the 2D non-separable filter. It's a direct implementation, it's an optimized implementation with reduced initiation interval, and it's a fast implementation where I use input data in maximum width equal to 128. So also I have a test bench with input image, and this test bench will produce 2 output image. First output image could be used for checking direct implementation or implementation with reduced initiation interval, and the second one image could be used for checking fast implementation of the 2D non-separable filter. Also, I have a MATLAB script. In this MATLAB script, I just read hardware output, I produce my own software output, and then I could compare all 3 images. I'm not going to show you right now source code for do this function. So if you are interested in this kind of implementation, you just please contact me by using email or in comments, and I will tell you how can you get all these sources. I mean Vivado HLS project and MATLAB script. So feel free and ask any question.